So vectors. As we've learned before, a vector is a quantity with size, that's magnitude or numerical value, plus a direction, whereas a scalar is a quantity with size only. The vectors we've had so far are like displacement, velocity, and acceleration. Other vectors that we'll have in the future: force, momentum. Force will be a big one, but we'll talk about those later. Scalars are quantities with size only. Some of the scalars we've had so far are distance and speed, time, mass, and there'll be others as well. Now with vectors, we're going to focus on vectors here. Vectors, symbolically, when we're doing diagrams, we're going to use arrows to represent vectors because arrows have the two aspects that we like to demonstrate with vectors. They have a size, how long we draw them, and they have a direction. They have an arrowhead. So the arrow will be our pictorial form of a vector, but also in printed form sometimes, and different books vary on this. In a lot of books, vector quantities symbolized with letters like A or B or C will be in bold print like you see here. Sometimes they have a little symbol over the top that looks kind of like a half arrow, kind of like this. That means they're vectors. They have a size and direction. I'm not sure what happened to my notations here, but the degrees were left off of all these. This is supposed to be 10 meters at 40 degrees. That's our direction. We're going to use angle measurements up to 360 positive and negative for our, that's supposed to be a degree. Let me erase that. So now I'm going to show you how to draw these, and we'll be doing a worksheet on this. So for example, vector A is a 10 meter vector, and we're not going to draw it 10 meters long because that wouldn't fit on a page. But the basic idea is this: if we draw a basic Cartesian coordinate system where you have your four quadrants, our standard will be this. This will be the 0 degree direction, the positive x direction, that's 0 degrees. North is 90 degrees. Now if you're a pilot in an airplane, I guess they use north as 0 degrees and then they adjust these accordingly, but this is 180 degrees, 270 degrees, and if you go around full circle you'd get back to 360 degrees all the way around this coordinate system. So now we'll sketch the vector. It's a displacement vector. You can see by the fact that it's 10 meters. Meters is a distance, but we also have the direction 40 degrees. So I'm going to sketch the vector. That's 10 meters at 40 degrees. You don't need to use a protractor for this. And obviously you're not drawing it 10 meters long, but it's a scale diagram. For example, we can compare this to vector B. I'll draw the coordinate system. Eventually you're going to stop drawing the coordinate system and just sketch the vector without all the, the 0, the 90 to 180. That's all understood and assumed. But vector B is half as long, and it's at 125 degrees. 125 degrees is 35 degrees past the 90 degree mark. Just estimating, it's right off in this direction. So the small acute angle with the positive y-axis would be 35, but the overall angle from the positive x-axis is 125 degrees, and then the vector itself is 5 meters long, half as long as vector A. Now vector C is not a displacement vector, so you really can't compare it to the first two. It's a velocity vector. Once again, you can tell by the units, but if I simply sketch a coordinate system, but what I want to show you here is that you can note these angles with negatives as well as positives. For example here, vector C, negative 135 degrees. So if you start at the positive x-axis and you go negative 135, so if you come this way around 135 degrees, because the negative y-axis is negative 90 degrees per se, and I'm going to draw the vector. That red arc I drew was the angle. So there's the vector starting from the origin once again. That's 12 meters per second. and the angle is negative 135. So you can do it that way as a negative 135, or you can do it as positive 225. As you will also see, if you take 225 plus 135, that gets you a full 360 degrees. It's 225 degrees from the positive x-axis. Okay, so we've learned how to sketch vectors. Now what we'll need to do is to be able to break a vector down into its pieces. It's called vector components, or sometimes called vector resolution. So I will do all three vectors that we just drew. We'll do the vector resolution. And this is basically trigonometry. Your SOHCAHTOA, sine, cosine, and tangent trigonometry. Once you have the vector drawn as you do in the upper part here, but I will just make a quick resketch of the first vector. Without all the numbers. What you want to do is look at the origin and break the vector into what we call two components, the x and y components, lining up with the x-axis and y-axis. And it'll look something like this. The x component will be along the x-axis and the y component on the y-axis, but they're just long enough such that they would form a rectangle with the actual vector as the hypotenuse of the rectangle. And the hypotenuse, or the vector itself, would then split the rectangle into two triangles. So we're going to call this bottom vector here a sub x. It's the x component of the vector A. And then we have a sub y, which is the y component of the vector. We're probably not going to be drawing these little vector hats or arrows, half arrows on top of the vector every time. It's understood that we're dealing with vectors here. But this is SOHCAHTOA. For example, the angle here, which is 40 degrees, let me try to squeeze that in, 40 degrees right there. If I was looking at that bottom triangle, if I take the cosine of 40, if I take the cosine of 40 degrees, that's the adjacent leg, which is a sub x, over the hypotenuse, which was the vector itself, which was 4 meters long. Excuse me. It was 4 meters long. And now I solve for a sub x. A sub x is going to be equal to excuse me, 4 times the cosine of 30, 4 times the cosine of 40, which is, if you do it in your calculator, that would be 3.06 or 3.1 meters. And the direction is implied as the positive x direction. So that's your x component of vector A. So for the y component, once again, if you look at that triangle, and maybe I'll outline it in black here. If you're looking at this triangle right here as a right triangle, this leg on the right hand side is the same height or length as the x component or the y component, which is on the y-axis. But if I'm looking at that black triangle, if I want to figure out that short leg that matches up to a sub y, it will be the sine of 40. So if I take the sine of 40 degrees, that will be a sub y over the hypotenuse of 4. And to solve for a sub y, it'll be 4 times the sine of 40. And that is 2.6 meters. So those are our two components. That's one of our jobs that we'll be doing. We'll be doing this a lot all year long, finding the components of vectors. Well, let me do the other two. Let me do B and C, just to show you how the negatives come into play here. I'll flip to a new page.